This next lesson is about radians. Let's jump down to the interactive panel here. We'll go across to radians and we'll click play. In this lesson, we're going to learn about a better unit to measure angles with. The unit circle is a good place to start using them because having the radius of one unit makes the numbers nice and simple while you get used to it. You're familiar with measuring angles in degrees. Just going to pop the lesson speed down there. Okay, so degrees, that's 60 degrees there. But really, degrees don't relate perfectly to circles. But really, degrees don't relate perfectly to angles or circles at all. The idea of dividing a circle into 360 degrees to use for angles is actually based on an outdated calendar system used over 2,500 years ago by ancient Babylonians. Right, this is the ancient Babylonian calendar. It's something like this. Back then, they noticed that the moons seemed to go from invisible to crescent and half moons, so like this, and then to full moons, and then back to invisible, every 29 and 30 days. And they noticed that the sun seemed to have its own pattern that created the seasons, like summer and winter. And back then, they had some idea of the moon and sun's orbits, but they thought they rotated around the Earth rather than the Earth rotating around the sun. So they thought the moon rotated around the Earth, which it does, but they also thought the sun rotated around the Earth, which makes sense if you're, if it's 2,500 years ago, but knowing what we know now, it's a bit silly. But they realized the sun's pattern would repeat roughly every 12 moon cycles. So if the moon went from invisible to a full moon and back 12 times, then the sun repeated its own cycle once. Drag the sun anti-clockwise around the Earth. Watch the counter on the sun, which counts how much of the sun's cycle has passed, and the counter on the moon, which counts how many of the moon's cycles have passed. Right, so if we drag the sun like this, look how the moon is rotating much faster, and now the moon has done one cycle, one rotation. And then we keep dragging the sun, and the moon's now done 2 rotations. We'll keep dragging around, 4 rotations, 5, 6, and the moon has done 6 rotations, and the sun has only done half a rotation. And then we'll keep going, 7, 8, 9, 10, 11, and then the sun has almost finished now. And the moon has done 12 of its own rotations in the time that the sun has done 1 rotation. So they're basically called one sun cycle a year and one moon cycle a month. This is actually the same reason that we still have 12 months in a year to this day. And if each of their months had around 30 days, 12 months times 30 days means how many days? Means they had how many days in a year? Oh, look at the formatting stuffed up there. Anyways, okay, so 12 months, 30 days in each month. That should be 12 times 30 is 360. I know that we have 365 days in a year now, but based on their old calendar, they would have 360 days. All right, drag the sun around the Earth again. This time keep an eye on the day counter on the Earth, okay? All right, well the Earth one's going much quicker. Okay, keep going. And by the time we hit here, halfway, we've got 180 days on the Earth. There we go, that's perfectly halfway there. Okay, and then we keep going. And we're like 3/4 of the way through the year now. And then we keep going all the way up to here, and 360 days. So there's our 360. But how does 360 days in a year become 360 degrees in a circle? Well, by splitting the year, the sun's orbit, into 360 days, they were kind of splitting this circle into 360 pieces. Centuries later, when the ancient Greeks were working on more complex maths and needed a better way to measure angles, they decided to divide a full rotation, like a circle, into 360 pieces that they called degrees, just like the Babylonians kind of did with days. Okay. And that's a decent system. 360 is actually a really nice number to work with. You can split it up into lots of different fractions, like 360 divided into two pieces is 180. So half a circle, 180 degrees, that's a pretty nice number. Dividing into four pieces gives 90. Okay, nice number to work with. Dividing into 8 gives 45. Dividing into 12 gives 30. Okay, all whole numbers, all really nice to work with. By the way, notice how these angles line up with angles in our exact value table. Interesting. So there's our 90, I think we did 60. Maybe not. But yeah, 45, 30. And actually, 360 can be divided by all of these numbers here and more. Obviously, like all the whole numbers. These are all the whole numbers that can be divided by. And you'll get other whole numbers. So yeah, really nice amount of options. So it's not a bad system. However, in reality, it doesn't make that much sense because Earth doesn't rotate around the sun every 360 days. It actually changes every year, but on average, it's approximately 365.2422 days. And the 0.2422, which is basically a quarter, is why we have a leap year every 4 years. Think about this. The Earth is just a big rock rotating around a massive ball of essentially fire. And so there's no reason why it should necessarily line up perfectly with these numbers, right? And so it's roughly this, and this is a terrible number to work with, and it's rounded, and it changes every year anyway. So it's just a very, very inaccurate, imprecise thing to base what we measure circle angles with. It's funny when you think about it like that. I mean, awesome for people who came up with this 2,500 years ago. It's insane how smart they were and how much they knew. But it's funny thinking about it now. Okay, and now we know that Earth orbits around the sun, and Earth's orbit isn't even a circle; it's an ellipse, which is basically an oval. So it's not even a circle. So it's really silly to base all of this off of off of that. Also, like we said earlier, the moon cycle isn't exactly 30 days either. It's between 29 and 30. Sometimes it's 29, sometimes it's 30. It's usually in between somewhere. Yeah, all very imprecise. So the 360-degree system can be nice to work with, but it's based on some inaccurate maths from thousands of years ago. And based on moon and planet orbits that aren't even circles. So since then, humans have come up with a much more accurate way to measure angles. Now, obviously we still use degrees, and degrees are awesome. And 360 degrees in a circle, it's great. And they use it heaps in like navigating different places, and especially on boats, navigating boats, and it's great. Okay, but there is also another system that we're about to use now that is a bit nicer to work with when we're just doing like pure maths. It's a little confusing at first, but once you get used to it, it makes a lot more sense than degrees. And it unlocks some much more complex maths that is 10 times harder if you're just using degrees. Instead of measuring in degrees, we can measure in radians. And rather than being based on roughly how many days Earth takes to orbit the sun, radians are based on the radius of a circle. That's why they're called radians. So there's the radius there. We're going to base how we measure angles based on this radius. For example, if we have our unit circle with a radius of 1 unit, and there's an insect here, okay, and it flies along the edge of the pond like this, all right, traveling a distance of 1 unit, then this angle here would be 1 radian. Okay, so if it's going to travel like this far, or this far, or this far, that'll be something different. But if it travels a distance that's equal to how big the radius is, then that would have traveled an angle. It would have like the frog would have to rotate 1 radian as an angle to keep up with it and still be facing it. So basically 1 radian is the angle created when the arc length is the distance along the edge of the circle, this is an arc here, is equal to the length of the radius. So if the insect flies another distance of 1 over to here, we'd have to rotate another 1 radian. Then when the insect has flown a total distance of 5 units, so all the way around to here, 5, so like 1, 2, 3, 4, 5. How many radians will we have had to rotate total? It kind of says the answer there, but yeah, it's 5. So 5 radians of rotation. So then how many radians in a full rotation? Looks like we can squeeze one more in, so we get to there. But what about this extra awkward bit here? Well, think about it this way. When the fly has flown the full distance around the circle, we would have rotated the full circle. So when it gets all the way up here, it's gone like the full distance around the circle. And if we're rotating to keep up with it, we would have rotated along with it, I guess. So the full distance around this circle would be equal to the number of radians in a full rotation. This distance around the circle is also known as the circumference, and you would have done that before. It's like the perimeter around the circle. And we can use the circumference formula to calculate it, and that one is C, circumference, equals 2 times pi, special number pi, times r, which is the length of the radius. I think I explained that here, actually. Yeah. R is our radius, which for R is our radius, which for the unit circle is 1 unit. So, nice. Exactly, the radius is 1. But because timesing by 1 doesn't do anything, we can just cancel it out in this case. Okay, so really this circumference here is pi just stands for a really complicated number. 3.1415926535 plus a lot more digits. But you can think of it in your head as roughly 3.14 or like a little bit over 3. It's like just above 3. But if we want to be accurate in our calculations, we can leave it as pi. Then when we put it into a calculator, we won't get any rounding errors. Okay, so if you use 3.14, and especially if you do some other calculations involving it, you'll get lots of rounding errors. So if we just leave it as pi, and most calculators have a pi button on them, then we round our answer at the very end if we need to. We're gonna not have rounding errors. And sometimes, especially with radians, we just leave the pi in our answer. So for this circumference, we could put 2 pi into the calculator and get C equals 6.283185307. But that's a lot of digits to write down, and even then it's not exactly correct because even the calculator had to round it because there's so many decimal digits after that. So depending on the situation, we might want to just leave pi in our answer, and with angles and radians, that's what we usually do. So let's leave this circumference as 2 pi, but we can think of it in our heads as 6.28 or just like a little bit over 6. Okay. So now we know the circumference of the circle is 2 pi, or just over 6.28, meaning if the insect flies all the way around the circle, all the way around here, it would have traveled a total distance of 2 pi. So 2 pi, or 6.28 units. So if this is a distance of 1, this is a distance of 6.28, or 2 pi, same thing. And that means we'd have to rotate a full 2 pi radians to follow it. Cool. I'm not sure if I explained it here, but this awkward extra bit, so we went around 6 units and 6 radians to rotate with it. And obviously the awkward extra bit is that 0.28. So 6.28 was the full thing, 6 was just here, the extra bit's 0.28. But yeah, if we go all the way around, we've gone 2 pi units, and so we also have rotated 2 pi radians. Now, what if the radius wasn't 1? Let's try a radius of 2. Trace out a new circle by dragging the log around. Alright, here we go. Now, let's find the circumference of this circle. First, type in the circumference formula. C equals 2 pi r. Make sure you use a capital C and just type in pi for pi. Okay, capital C equals 2 pi r. Now, because the radius of this circle is 2, the circumference will be 2 times pi times 2, which we can simplify to 4 pi. Go ahead and change that in the formula now. Okay, so r was 2, but then we can do 2 pi. 2 times 2 is 4. Nice, so the circumference of this circle is 4 pi. So does that mean when there's 4 pi radians, so does that mean there's 4 pi radians in this circle? Interesting. Well, remember that 1 radian is based on an arc length of 1 radius. Okay. So the insect would have to travel a distance of 2 this time instead of 1, while the frog would still rotate 1 radian. Okay, so because the radius is now 2, for the insect to have traveled enough for us to rotate 1 radian, it has to go 2 units this time, not just 1. But the frog is still only going to go 1 radian. 1 radian, okay. And if the insect did this 6 and a bit more times, so 2, 3, 4, 5, 6, and then a little bit more. Okay, I think I meant to say like 5 and a bit more times, but it's 6 and a bit total. So we do it once, twice, thrice, 4 times, 5, 6, and a little bit more. And the frog has only rotated, well, I guess it didn't really rotate with it, but if it was going to rotate, it would have to rotate 1 radian, 2, 3, 4, 5, 6, and a bit extra. The insect would have traveled the 4 pi, which is 12 and a bit, distance around the circle, but the frog would still have only needed to rotate 2 pi, which is 6 and a bit radians. So the radians stays consistent because even if the radius increases, the circumference will increase as well, but that just means we're going to travel even further to stay in line with it. But the radians you'll always rotate the same amount no matter what. So just like every circle has 360 degrees, every circle has 2 pi radians, no matter the size. Okay, so now you know about these more accurate units for angles, let's start using them. Also, a quick note on the notation, the notation for radians, like how we write it down. You might see the symbol, it's like a little C, it's like a power of C kind of. You might see that used sometimes. For example, 3 radians could be written as 3C. However, this is a little too similar to the degrees symbol. So you have the degree symbol there, and then the C there. It's like almost the same thing. It's really easy to get them confused. So these days, the official notation is just RAD for radians. So 3 radians would just be written as 3 rad, or sometimes, especially when pi is involved, we even drop the rad. So pi on 2 radians could be written as pi on 2 rad, or just pi on 2. Usually we get the idea with pi on 2. If you want to be really, really specific, you chuck the rad in if you're being careful or specific. But if you do see the C symbol every now and then, it's the same as using rad. Okay. So let's use radians to look at some of the common angles that we've been using in degrees. If a full rotation is 2 pi radians, what do you think half a rotation would be? Okay, well, full one's 2 pi, half would just be 1 pi, because then we go like 1 pi to get to here, and then 2 pi to get to there. So over here will be 1 pi, yeah. That's right, half of 2 pi would be pi, so half rotation is pi rad, pi radians. And for a quarter rotation, we can halve that again and get, okay, well, half of pi, we can just write it as pi on 2. It can't be just 2 because that's kind of meaningless. And if we think of pi as like, pi is about 3, 2 would be like there, roughly. That wouldn't work. And then pi is just there, and then 2 pi is all the way around. So yeah, pi on 2 would be just here, like half a pi. That's right, half pi would be pi on 2. So a quarter rotation of a full circle is pi on 2 radians. If we halve that again, half of pi on 2, that'd be like a quarter. But we want to keep it pi, right? So instead of pi on 2, pi on 4. That's right, half pi on 2 would be pi on 4. So this angle, an 1/8 rotation of a full circle, is pi on 4 radians. These last two line up with some of the angles from the exact value table. Yeah. So let's update our exact value table to have the angles in radians as well. Yeah, so 180 degrees was pi radians, 90 is pi on 2, and 45 is pi on 4. So let's update some of these. 90 degrees is pi on 2 radians. We'll pop that pi on 2 next to it. And 45 degrees is pi on 4, pop that next to it as well. And 0 degrees is also 0 radians, so we'll just leave that one as it is. Now let's do 30 degrees and 60 degrees, starting with 60 degrees, okay? As you can see from pi on 2 and pi on 4, it's helpful to think of these angles as fractions of pi. Because 90 degrees is half of 180, it makes sense that 90 degrees is pi on 2 radians. And 45 degrees is half of that, or 1/4 of pi of 180. So it makes sense that 45 degrees is pi on 4 radians. So for 60 degrees, let's think about what fraction 60 is of 180. Think about how many 60s fit into 180, then select the answer you think is correct. Okay, how many 60s fit in 180? 3. 3 60s. 60, 120, 180. So 60 is a third of 180. Nice, and that's why 60 degrees is pi on 3 radians. Okay, cool. So yeah, from here all the way up to here is pi on 3, or 60 degrees. Now for 30 degrees, you could do the same thing. How many 30s fit into 180? That would be 30, 60, 90, 120, 150, 180, so 6. You can just think about how 30 is half of 60. So we just halve pi on 3 to get pi on 6. Nice, and that's why 30 degrees is pi on 6 radians. Awesome. Now, all of the things we've learned so far about trigonometry, using the unit circle, we can also do using radians. Let's do them now so you can get used to using radians. It'll also be a good review of the concepts themselves so that we don't forget them as easily. Let's try typing in the angle to rotate the log to the insect. For this one, type in pi on 3, okay? pi over 3. Nice. For questions like this, the angles in radians are almost always related to the ones in the exact value table. So pi on 2, let's pull the list up here. Pi on 2, pi on 3, pi on 4, pi on 6, so all of these guys, 2, 3, 4, 5, 6. Oh, no 5, sorry. I say related because it might be something like 7 pi on 3, which isn't on the table, but pi on 3 is, and you can use that to solve it. The main point is that it's rare to see something like pi on 29. Depending on the type, but depending on the question. But we should start with the angles on the table before resorting to weirder numbers. That's basically the point. Now, you try these next 3 yourself. They'll all be angles that are on the table. Okay, so that one there, it looks like 30 degrees. So 30 degrees is the same as pi on 6. Let's do it. Pi on 6. Nice. Try this next one. Okay, this looks like halfway, which is 45 degrees. So that's pi on 4. Pi on 4. And if we're just thinking about radians and not even thinking about degrees at all, pi is all the way over here. And then this is like a quarter. So this is a quarter of the way over to pi. So pi on 4 makes sense. Get one more of these. This one as well. Let's think of it like there's pi. That's halfway to pi. So pi on 2. Nice. Now, let's do some that are above these basic angles. For this one, it looks like this could be, it looks like this extra bit could be pi on 6. Yeah, there's a small little pi on 6, which is the same as 30 degrees. So the easiest way I've learned to work this out is to split the circle up into slices of pi on 6. Okay. Interesting. Then count how many of those pieces we need to rotate. So for a positive angle, how many of these pi on 6 pieces do we need to rotate to? To get to this insect. Okay, we'll go 1, 2, 3, 4, 5. Exactly, and 5 pi on 6s would equal 5 pi on 6. Type in 5 pi on 6. Make sure you put the 5 and the pi in the numerator in the top together. So 5 pi over 6. Nice job. Try that method yourself to solve these next ones. Think about which angle to try splitting the circle into, then count how many of those you would need. Okay, well this one is kind of already split for us, but how big would each one of these be? Well, let's think of pi. Pi is over here. How many pieces is pi split up into? So it's this first half rotation like this. That's a 1, 2, 3, 4. So each one of these is pi on 4. And then we use 1, 2, 3. So 3 pi, oops, 3 pi on 4. Cool. Okay. Try this next one. Okay, all the way down here. Let's think about pi. Pi is split up into 1, 2, 3, 4, 5, 6. 6 pieces, so pi on 6. And then we need to go 1, 2, 3, 4, 5, 6, 7 to get around to our insect. So 7 pi on 6. Cool. Awesome. One more of these. Try picturing the segments yourself this time. For this one, you could count in pi on 6s or pi on 3s. Both are fine, just make sure you simplify the fractions you count pi on 6s. Interesting. So, okay. This segment. So this big piece here looks like it could be there, and then that's a big piece, it'd be like 2, 3. So it looks like we could split it into 3 pieces like this, like that. 1, 2, 3. So pi on 3. And then it would take 2 pi on 3 to do that. And then I want to explain the pi on 6 thing here. You can also split it into pi on 6s like this, there, and then there, and then there, and then at 1, 2, 3, 4, 5, 6. And then you would need 1, 2, 3, 4. So you would need 4 pi on 6, 4 pi on 6. But then we would want to simplify this fraction. You could divide 4 and 6 by 2 to get 3 and 2. So you get 2 pi on 3 anyway. So it's best to use the the simplified fraction, or use like the biggest segment that makes sense to use. But yeah, let's submit that one. Awesome. Now try negative angles for the next ones. I'll draw the pieces for the first ones to help. Put the negative sign at the front of the fraction, not in the numerator or denominator. Right, so we put a negative here and then we do our other stuff. Cool. So, negative angle. So, how many pieces do we need? We need 1, 2, 3, 4. So it should be 4 pi on, and then pi itself, so this half rotation is split up into 1, 2, 3 pieces. So 4 pi on 3. Alright, try this next one. Okay, we're down here using a negative angle. We're using 1, 2, 3, 4, 5. I guess let's think of how many it's split up into first. So pi itself, all the way around, is split up into 1, 2, 3, 4, 5, 6. So it's going to be pi on 6. And then we're using 1, 2, 3, 4, 5. We're using 5 of them, so 5 pi on 6. But it's negative, so negative 5 pi on 6. Awesome. Last one. Try picturing the segments yourself this time. Oh, goodness. Okay, so this part here could be a segment, and then like that. And then if we use the same size segment, maybe it's like this, like that. And 1, 2, 3, 4. I think that works. Maybe it looks like it could be 3 as well, but I think if you split it into 3 segments like this, and then we have 1, 2, 3. That's, yeah, it's not quite. It's too big. So I think it's 4. So we have 4 segments for each pi. That means pi is split into 4 pieces. And then if we're going to work our way around, we go like there's that, like that. So 1, 2, 3, 4, and then 5, 6, and then 7 would get us to here. So 7 pi on 4, but it has to be negative. So negative 7 pi on 4. Okay. That was a tricky one. Awesome. We can also use our calculator to calculate side lengths using radians instead of degrees. First, work out this angle in radians and type it in. Use a positive angle. Okay, so it looks like this one would be 3 segments. 1, 2, 3. So, and we're going to use one of them. So it will just be pi on 3. Nice. Now let's find the horizontal length using a calculator. Type cos and then pi on 3 into your calculator, then type the result below. Now, very important, make sure your calculator is in radians mode. Ask your teacher or Google it if you don't know how. So, for example, if I have my calculator and the model of my calculator is TI-84 plus CE. It says it on the top of your calculator somewhere. So I can go onto Google and I can look up TI-84 plus CE, and then I can look up like radians mode or how to change into radians. And then, well, you can try the AI review, or you can grab the video that comes up with a suggestion. Yeah, any of these videos will be fine. Although maybe that one is wanting you to convert. So maybe like, maybe change into radians mode might have been a better search. Yeah. And so I'll do that on mine now. Let's see how good the AI overview is. Press the mode key. Okay, I got mode there. Use the arrow keys to highlight radian. And then press enter. Okay, that worked. Nice. But yeah, and the other main model that we use in Australia, in Queensland, is Casio something. So you just look up Casio, yeah, I think FX-CG50. That sounds familiar. That's the other one. And so just look up what calculator model and then follow the instructions. And that works for anything, by the way. Like if you want to find out like how do I graph something on the calculator, blah, 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 just look up your calculator model and then how to blah, blah, blah. There's a bunch of YouTube tutorials. Sometimes, I mean, the AI reviews decent at this stuff. And then also you can find like the actual, what's the word? Manual, the actual manual for the calculators. And that can be helpful too. Usually the YouTube ones are good to use. All right, so now that my calculator's in radians, I can do cos of pi on 3. Oh, and the other thing to be careful of, by the way, is sometimes you will go back to working in degrees. A lot of bearings questions that you'll do later on will involve degrees. So if you get weird answers for that, it's very common that, oh, I forgot to change my calculator between degrees and radians. So if you ever get a weird answer, just double check that your calculator's in the right mode for what angle unit you're actually using. Anyways, cos pi on 3, 0.5. Nice. Now let's find the vertical length. Type sine of pi on 3 into your calculator, then type the result below. Okay, sine pi on 3. 0.87. Nice. Let's try some weirder angles now. Okay. This angle is 3 pi on 5. Type it in. Okay. 3 pi on 5. Is that in our exact value table? No, we have 2, 3, 4. We don't have a 5. So this is for ones that are not the normal segments, I guess. Nice. Now find the horizontal length using a calculator. So it's still going to be cos. Cos, it's just now we're entering it in radians. 3 pi on 5. Negative 0.31. Okay, cool. And the vertical length, we just want to do sine of 3 pi on 5, 0.95. Okay, so yeah, same as we're working with degrees. One more, this time we'll use a negative angle and find tan theta instead. This angle is negative 6 pi on 13, type it in. Negative 6 pi on 13. Nice, now use a calculator to work out tan theta and type it in. Okay, so tan, and the angle is negative 6 pi on 13. Negative 8.24. Cool. Yeah, and remember the tan theta is like the gradient, and it makes sense that it's going down quite sharply. Down if you're going from left to right, which is what we have to do, the gradients. Cool. Great work. Next, we'll use the exact value table to solve for an unknown angle. Ooh. Imagine the question was sine theta equals negative 1 on 2. These are from the last few chapters that we were doing. All right, because sine is for the opposite, and in the unit circle, the vertical side, this tells us that the angles we need will result in an opposite length of negative 1 over 2. Okay, so the frog went down 1 on 2, like this, and goes either left or right. Okay, meaning it could be in one of these two positions. All right. So, using radians, find the two possible angles for theta, starting with this first one. Use a positive angle. Okay, so pi on 2, okay. Well, it's not pi on 2, sorry, 1 on 2. Well, let's go to our exact value table. For sine to give us a 1 over 2, sine 1 over 2, we have to use 30 degrees, or in radians, we have to use or involve pi on 6. So if we cut the circle into pi on 6 pieces, like cut pi into 6 pieces, then we need 1, 2, 3, 4, 5, 6 to get around to pi. And then we need an extra pi on 6. So that should be 7 pi on 6. Tricky one. Nice. So we can write our answer to the question as theta equals 7 pi on 6. Type that in. Remember, for theta, you just type in the word theta. So theta equals 7 pi on 6. You could, if we really want to specify, we could say rad at the end, radians. Don't do that here because the computer wants, I think, exactly this answer. But if you're feeling like you really need to specify an exam, or you notice that your teacher or the questions you guys are working on, they want you to specify these angles using like the actual units of RAD, go for it. Sometimes they don't need that because it's assumed, it's mostly because the pi is in there, we kind of know what it is, but yeah. Nice, now find this second possible angle. Okay, well, I can still count around, so we get 6 to get to here, and then 7, 8, 9, and then 10, 11. So 11 pi on 6. Another way we could do it is think about this is pi on 6 in here. If we went all the way around, it'd be 2 pi, and then we have to come back pi on 6. And so one way we could do that is think about how the total would be 12 pi on 6s. If we go back by a pi on 6, that would only be 11 pi on 6. So that's probably a slightly better way, but also counting around is a really nice way, especially when you're starting out, just getting used to it. Nice. Let's try a couple more. So cos theta equals root 3 on 2, all right? Because cos is for the adjacent, and the unit circle, that's the horizontal side. This tells us that the angles we need will result in an adjacent length of root 3 on 2. So if the frog went to the right by root 3 on 2, okay, and goes either up or down, meaning it could be in one of these two positions. All right. So using radians, find the two possible angles for theta, starting with this first one. Use a positive angle. Okay, so the cos to give us root 3 on 2, cos root 3 on 2, it's going to use 30 degrees or pi on 6. Oh, pi on 6 again. So we have to use pi on 6s, and just straight up, it's just going to be pi on 6 for this first one. Pi on 6. Nice, so we could write our answer to the question as theta equals pi on 6. Type that in. Theta equals pi on 6. Nice, now find this second possible angle. Okay, let's try it the way I was talking about. So if pi on 6 is in here, then we could go all the way around to 2 pi and then come back pi on 6. But to keep everything in pi on 6, think about 2 pi, that would be 12. 12 pi on 6s to get all the way around to here. And then going back by pi on 6, that would mean 11. 11 pi on 6. And again, if you're using the counting way, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And if it's still not kind of working in your head, just draw a circle on your page in your book, and then split it into split each pi into 6 pieces, and then count your way around doing that. That's what I would do. Until you get used to being able to draw it in your head, or until you get used to being able to go to all the way over to 12 pi on 6 or 2 pi, and then going back. Let's use negative angles for this last one. Okay, cos theta is negative root 2 on 2. And cos is the adjacent, so the horizontal in the unit circle. Angles we need will result in an adjacent length of negative root 2 on 2. So again, if the frog went to the left by root 2 on 2, and it goes either up or down, meaning it could be in one of these two positions. Okay, there we go, nice. So find the two possible angles for theta, starting with this first one. Remember to use negative angles for this one. Okay, so cos root 2 on 2, that will have to involve pi on 4. So how many pi on 4s do I need? If I think about pi's over here, split it up into 4 pieces. We got like 1, 2, 3, and then 4. And so we want to go 1, 2, 3. So it'd be 3 pi on 4. And remember to use negative angles, so we put a negative out the front here. Beautiful. Nice, so we could write our answer to the question as theta equals negative 3 pi on 4. Type that in. So theta equals there. Nice, now find this second possible angle. Remember to use a negative angle still. Okay, so pi is in 4 pieces, so like 1, 2, 3, 4 pi on 4, and then 5 pi on 4. And don't forget, Michael, to use a negative. There we go. Nice, so then we could also say theta equals negative 5 pi on 4. Type that in. Okay, theta equals negative 5 pi on 4. Nice. Awesome stuff. Lastly, let's look at multiple rotations and domain. Imagine we had a question similar to those last questions, but this time we're given a domain that our angles have to be within. So like sine theta is 1 on 2, but theta has to be between negative 5 pi and 3 pi. And again, it's usually easiest to find the positive angles first, then find the negative angles. So what's the first positive angle that would work? Oh, you're not even going to draw it out for me? Okay. So sine is the opposite. So in the unit circle, that's up and down. And it's going to be 1 on 2. So it'd be like somewhere here. Like in between. Like we don't know what cos is, so it could be over here or it could be over here. Those will both give us a opposite length of 1 on 2. Okay, and then the first, well, we have to get our reference angle. So to get sine to be 1 on 2, sine 1 on 2, we have to use pi on 6. And then it's positive, and we're allowed positive angles, so we can just straight up just use pi on 6. So pi on 6 will be our first one. Nice. Okay, now we're going to see it drawn out. But yeah, we'll get us to there. Now work out the next one and type it in. Okay, so all the way over here now. And if that over there was pi on 6 in there, this should have to be pi on 6 in here. So we can think about going all the way over to pi. And if we're talking about pi on 6, pi would be 6 pi on 6s to get all the way around. But then if we're going to go back by pi on 6, we only need 5 of them. Okay, nice. You could also count your way around. So like 1, 2, 3, 4, 5. That also works. Now to figure out if we can use a second full rotation to find more angles that work. We would usually add 360, but in radians, we add 2 pi, a full rotation in radians. So we can just add 2 pi to each of our answers. However, because we're dealing with fractions, they have to have the same denominator. So they have to have the same bottom number before we can add them. So because our angles are something over 6, we need to make 2 pi be something over 6. Kind of like what I was saying here with like the 6 pi on 6. So we just times 2 pi by 6 to get 12 pi, and then put it over 6 to get 12 pi on 6. And now we can add it to our angles more easily. And we can verify that because 12 over 6 would simplify to 2. So just a different way of writing 2 pi, but now it's over 6, so we can add and subtract it with other things like pi on 6 and 5 pi on 6 more easily. So our first angle pi on 6 worked. Let's add our 12 pi on 6 to it to get our next angle of 13 pi on 6. So 1 pi plus 12 pi is 13 pi. 13 pi on 6. Nice. Now, to check if the next angle is within the domain of 3 pi, it helps to ignore the pi for a moment. So for that last angle, 13 pi on 6, we could have checked it by comparing just the 13 on 6 with the 3 in the domain of 3 pi. Interesting. So is 13 on 6 less than 3? You could use a calculator, or you could convert the 3 to be over 6 as well. So this 3, let's think about that over 6. So you could times the 3 by 6 to get 18, then put the 18 over 6, because 18 over 6 is the same as 3. But now we can compare them. Yep, we can compare 13 on 6 with 18 on 6, and easily see that 13 is less than 18. So we can see that the angle of 13 pi on 6 is still within the 3 pi domain. Okay, that was a lot, but you'll see how it works as we go through it. So now add 12 pi on 6 to the second angle we got, which was 5 pi on 6, to get the next angle, and decide, does that fit within the domain? Right, well, we've got 5 pi on 6, we're adding 2 pi, which is 12 pi on 6. 12 plus 5 is 17, so 17 pi on 6 would work. But does it fit in the domain? Well, if we change 3 to be over 6, it'd be 18 over 6, and the 17 is less than the 18, so yeah, it does fit. That's right, 5 plus 12 is 17, so 5 pi on 6 plus 12 pi on 6 is 17 pi on 6. And because 3 pi is the same as 18 pi on 6, 17 pi on 6 is still within the domain. What a mouthful of a sentence those were. Okay, 17 pi on 6 still fits. Gotta remember to breathe through as I'm talking through these sentences. Great job. Now, if we kept going to get the next positive angle, would it still fit inside the domain? So add 2 pi, or 12 pi on 6, to the 13 pi on 6 we got here. So 12 plus 13 is 25. And remember, the 3 pi is like 18 pi on 6, and 25 is bigger than 18. So no, that one wouldn't fit. That's right. The next positive angle would be 25 pi on 6, which is bigger than that. So we found all the positive angles. Cool. Let's check for any negative angles now. Let's reset the log to 0. Okay. What would be the first negative angle that would work? Whew, okay. This time we have to go all the way around here. And the first one we hit will be this guy here. Using pi on 6s, we could think about, here would be 6 pi on 6, and an extra one would be 7 pi on 6. Also, we could count. So we could go 1, 2, 3, 4, 5, 6, 7. So either way we get 7. And then negative 7 pi on 6. Great job. Now, if we kept going to get the next negative angle, would it fit inside the domain? Interesting. So if we kept going all the way around here, what would this one be? Well, all the way around would be 12 pi on 6, and then going back a little would be 11 pi on 6, like negative 11 pi on 6, obviously. And is that less than 5? Well, the 5 we can convert to being over 6 as well. 5 times 6 is 30. So I think this one would be 30 pi on 6. So as long as our denominator is below 30, we're good. And 11 is, so yeah, we're good to go. That's right, so what's the next angle that would work? Another thing you could think about is negative 5 pi lets us do one rotation of 2 pi, another rotation of 2 pi to get to 4 pi, and then another one to get to here to 5 pi. And so we're good for a little while. We're good for at least 2 rotations, and then it's that third rotation we need to be we need to be careful on. But yeah, you can also compare it to the numbers. Anyways, negative 11 pi on 6. Okay. Great job. This time we minus the 2 pi, or the 12 pi on 6, from our angles to get the next rotation. And we compare it against the negative domain of negative 5 pi on 6, or negative 30 pi on 6, same thing, because 30 over 6 is 5. So, if we kept going to get the next negative angle, would it fit inside the domain? Now, I know I said minus the 2 pi, the 2 pi, or the 12 pi on 6. Honestly, in my head, I think of 7, and then I add 12 to it, and then I put the negative back on. It's the same thing. So we have the 7, we put an extra 12 on that, that'd be 19, and then with the negative back on, so negative 19. And that is still less than the 30 that the 5 would turn into. So yes, it fits. That's right, so next negative angle would be negative, what did I say? 19 pi on 6. Cool. And like I said as well, 5 pi is like 2 full rotations and then a half extra. So this is our second rotation, so anything in here should work. Great job. Now, if we kept going to get the next negative angle, would it fit inside the domain? I just said it should. Thinking about numbers as well, that one was, can't really see it, but it's 11, negative 11. An extra 12 on that would be 23. That's less than 30, so yes, we're good to go. That's right. What's the next negative angle that would work? Negative 23 pi on 6. Beautiful. Whoa, whoa. This is so hectic trying to fit all these angles in here. If you look at it for too long, it gets really concerning. Great job. Now, if we kept going to get the next negative angle, would it still fit inside the domain? Interesting question. So I just said negative 5 pi is like 2 rotations and then a half rotation, and we wouldn't be able to keep going, so we'd miss out on that one. Thinking about numbers, we get the 19 and add 12 to it, which would be 31, and that's bigger than the 30 that the 5 is. So, no, would not fit. Yeah, so the next angle that would work would be negative 31 pi on 6, but negative 31 pi on 6 is bigger than 5 pi, or negative 30 pi on 6. So we found all the answers for this question. Nice. Nice, so try this next one yourself. Remember that to find the extra angles, we can add 2 pi, and it helps to convert things into fractions with the same denominator, so we can add and minus them easily. So you can change the 5 into being something that has the same fraction as whatever reference angle we're going to use. Whew, okay. Press next. What's the first positive angle that would work? Ooh, use our brains here. So negative root 2 on 2 means it's going to go, well, it's sine, so we're using up and down, so it's going to go down to here, and then left or right from there. And we're using positive angles, so we're looking for this one first. And for sine to give us root 2 on 2s, we have to use pi on 4s. Okay, we have to count in pi on 4s till we get over to here. So 1, 2, 3, 4, and then 5. So 5 pi on 4. Whoa, what happened with the formatting there? There's one time where the formatting can be a bit weird. So use the clear button. If you really can't get it, figure it out, or it's being really glitchy, you can press the skip button to do that. But I think I can just backspace here. I'm not sure what happened there. Maybe I typed it too fast or something. What did happen there? Let me clear that. 5 pi on 4. That's really weird. But anyways, if it does get super stuck, you can press the skip button. Very nice. Awesome. Now, what's the next positive angle that would work? Right, so if it's down there, we could also go over here. So, two things. We could think about going all the way to 2 pi. And 2 pi in pi on 4s would be 8 pi on 4. So you need 8 of them to get all the way around. So if we went around 8 of them and then came back, that would be 7. So 7 pi on 4 should work. Also, if we're counting, we can go like 1, 2, 3, 4, 5, 6, and then 7 to get to there. Great job. Now, if we kept going to get the next positive angle, would it fit inside the domain? Yeah, well, 5 pi is at least 2 rotations and an extra half, so definitely will be fine. Let's say yes. But also, we could have checked by, which we have to do now anyway, by adding 2 pi onto the 5 pi on 4. And 2 pi, in terms of pi on 4s, that would be, so 8 pi on 4, and then add the 8 pi on 4, that's 13 pi on 4. So I'll type that in. If we wanted to check it against the 5 pi, we have to make the 5 pi be over 4. That would be 20 pi on 4, and the 13 is less than the 20. So we're good. Great job. Now, if we kept going to get the next positive angle, would it fit inside the domain? Well, 7 plus an extra 8 would be 15, and that's less than 20, so yeah. That's right. So what's the next positive angle that would work? What did I say? 15 pi on 4? Nice. Beautiful. Great job. Now, if we kept going to get the next positive angle, would it still fit inside the domain? Okay, so 2 ways to think about it. We've got the 2 rotations to get us to 4 pi, and then an extra pi to get us to 5 pi. We'd have to keep going past that to get to that one. So no, it wouldn't fit. You can also think of it comparing the numbers. So 13 pi on 4 plus 8 pi on 4 is 21. And that's bigger than the 20 pi on 4, which the 5 pi would be. So, no. So the next one would be 21, which is bigger than the 5, which is like 20 pi on 4. So we found all the positive angles. Let's check for any negative angles now. Let's reset the log to 0. Okay. What would be the first negative angle that would work? We just have to get down to here and using pi on 4. So that should just be 1. That's easy. So negative pi on 4. Awesome. And I think there might be one more based on this. let's check it properly. So if we did the next one, would it fit? So we're going to get around to here. We can just count with this one. So 1, 2, 3. And 3 pi on 4 is less than pi, because pi would just be 4 pi on 4. So yeah, that one fits. So negative 3 pi on 4. We could also go around to 4 pi on 4 and then come back pi pi on 4 to get the 3 pi on 4. And looks like we've probably found all of them, but let's double check anyway. 2 ways, so negative pi, that's just a half rotation, so there, and then we're pretty much already there by doing that, so probably not going to work. But yeah, thinking about how we'd have to go all the way around here, that's 2 pi, and an extra bit, it's not going to work. Thinking about just the numbers, negative pi on 4, and then if we put an extra 8 pi on 4, which is 2 pi, and that would be negative 9 pi on 4, and this is 4 pi on 4, so 9 is bigger than 4, so no, that would not work. Yeah, that's what I just said. So we found all the answers for this question. Cool. Okay, that's it. That's why we use radians, that's what radians are, and how to use them with all the unit circle stuff we've learned so far. That was a long one. Let's let Mr. Frog sleep. Right. Whoa, look at all these things we did. And we unlocked the final level. That's going to keep going for a little while there, so I'll just explain. We've got the practice questions down here. If you're not sure what to do on them, don't forget we have the video explanation there. And we got all the questions here you can do. There's quite a few of them there. Once you finish all of them, tick this one off and move on to the next one, which is converting between radians and degrees.